Welcome, everyone. I'm Ty Fountain, and I'm joined with Megan Reed and Trent Walker to discuss STOVL propulsion and its application. STOVL stands for Short Takeoff and Vertical Landing and allows aircrafts to operate from areas that lack conventional runways, such as an aircraft carrier. It combines the benefits of a helicopter's vertical lift capabilities with the speed and range of a fixed-wing aircraft. Compared to vertical takeoff and landing, VTOL, STOVL has a greater payload capacity, which makes this system useful for military applications as well as civilian applications. The interest of STOVL propulsion arose in the early 20th century, with initial attempts to create an aircraft capable of vertical takeoff and landing. The British Hawker P1127 was one of the first VTOL aircrafts that was implemented into the military. It brought forth a call for more aircrafts that could operate in a confined space. The Hawker P1127 utilized a Rolls-Royce Pegasus vectored thrust engine, a world's first designed specifically for VTOL and STOVL operations. Several early-stage aircrafts utilized the Pegasus vectored thrust engine. The Hawker P1127 Harrier Jump Jet and AV-8B Harrier II. This breakthrough engine design utilized four swiveling nozzles, which could direct thrust downward for lift and backwards for forward flight. The Harrier Jump Jet, developed in the 1960s, was based on the Hawker P1127 and utilized the same vector thrust engine from the Pegasus. To become the first, only truly successful STOVL aircraft of its time, this aircraft had a significant impact on military strategies worldwide, allowing for operation off aircraft carriers in the deep ocean, forward bases, and improvised airstrips in remote locations. The Harrier Jump Jet was the first of two generations from the Harrier family, with the second being the AV-8B Harrier II. With the rampant success of the Harrier Jump Jet, there was a call for a new aircraft that could outperform in terms of payload capacity and range. The Harrier II, introduced in the 1980s, was the answer to this call. It featured improved aerodynamics, greater payload capacity, advanced avionics, and extended range over the original Harrier. Both Harrier aircrafts introduced new military strategies to the world and brought forth a new era of aerospace innovation.
So how does a STOVL aircraft actually produce the lift necessary for flight? These aircraft generally have divertless supersonic inlets at the front of the plane, which compress the intake air and slow it down from supersonic to subsonic speeds before going through a turbofan engine. A lift fan behind the cockpit operates like a helicopter inside of the plane. It creates a lower pressure region inside the plane, sucking air through the aircraft by 90 degrees from above. This can produce around 80 kilonewtons of thrust, ranging from 70 to 90 depending on the specific plane. The jet flow under the aircraft produces a fountain upwash, which creates the lift necessary for vertical takeoff and then stability during vertical landing. This phenomenon is called ground effect and also allows the aircraft to hover. The general aerodynamic force and moment equations can be used to simplify the physics of flight with three axes, roll, pitch, and yaw. However, in order to model STOVL flight, the equations get much more complicated with engine thrust vectors in three-dimensional space and ground effect, which is dependent on altitude, Mach number, and the deflection angle of the nozzle. The F-35B Lightning is another incredibly well-known STOVL aircraft. It was the first aircraft to achieve all short takeoff, supersonic flight, and vertical landing all in the same flight. Other STOVL aircraft could achieve the short takeoff and vertical landing aspects, but were not capable of supersonic flight as well. The F-35 is a fifth-generation joint strike fighter with two internal weapon bays, armed with joint air-to-surface standoff missiles and long-range anti-ship missiles, which are precision-guided to counter attacks directed at U.S. ships at sea. They can achieve speeds up to Mach numbers of 1.6 and acceleration forces up to 7 Gs. The F-35B has an integrated system, shown on the right, with a turbofan, a 5-stage compressor, vertical lift fan, swivel duct, nozzle, and roll control ducts. The vertical lift fan, located toward the center of the aircraft behind the cockpit, provides vertical thrust needed to lift off. The swivel duct rotates at two different locations, 45 degrees each time, to configure the nozzle in a 90-degree orientation perpendicular to the ground to exhaust from the turbofan engine. And then the roll control ducts bleed air from the main engine directed downwards to the ground to provide lateral stability and rolling moment while the aircraft is hovering. This video shows the general lift and landing of the F-35. The video here showed the two supersonic inlets on the sides of the nose which suck air into the engine. And then when the plane is ready for takeoff, the hatch opens on the top of the aircraft to allow the vertical lift fan to pull air from the surrounding air as well. The nozzle rotates 45 degrees down and then 45 degrees again until it's at a 90-degree angle, able to take off completely vertically. And then the process is reversed for vertical landing.
Next, we have the Bell Boeing MC-22 or the CV-22B Osprey. The Osprey is used by three military branches: the Navy, the Air Force, and the United States Marine Corps. This airplane uses tilt-rotor technology in which it can fly both like a helicopter and like a fixed-wing plane. This allows it to use both STOVL and VTOL operations depending on payload or accessibility to runways or needs of transportation. This aircraft is equipped with two Rolls-Royce AE 1107C turboshaft engines that is capable of producing over 6,000 horsepower to each propeller. The only reason why we included this is because it uses STOVL when needing to carry heavier payloads, which would be expediting supplies or personnel. Next, we have the advantages of using STOVL technology. STOVL aircraft can operate from a variety of platforms, including conventional runways, short runways, and even small ships. This flexibility allows them to be deployed in various missions and terrains. Next, we have the accessibility of using this technology. STOVL aircraft can access areas that are inaccessible to conventional aircrafts, such as confined spaces, rugged terrains, or areas with limited runway infrastructure. This capability is particularly valuable for missions like close air support, reconnaissance, and special operations. Next, it can reduce infrastructure requirements. Because they can take off and land vertically or in short distances, STOVL aircrafts require less infrastructure compared to traditional fixed-wing aircraft. This makes them suitable for operations in remote or austere environments. The next is it provides a rapid response. STOVL aircraft can be rapidly deployed and repositioned, allowing for quick response to emerging threats or changing operation requirements. Their ability to operate from forward operating bases or dispersed locations enhances their responsiveness. The disadvantages of STOVL technology include the payload and range limitations. STOVL aircraft typically have reduced payload and range capabilities compared to their conventional counterparts. The design compromises for vertical or short takeoff and landing can restrict the amount of fuel and ordnance that can be carried. Next, we have the performance disadvantages. STOVL aircraft often sacrifice performance characteristics such as speed and maneuverability to achieve vertical or short takeoff and landing capabilities. This can impact their effectiveness in certain mission scenarios. Next, the cost and complexity. Developing and maintaining STOVL capabilities adds complexity and cost to aircraft design and operation. The engineering challenges involved in achieving vertical flight capability, as well as maintenance requirements for systems such as thrust vectoring nozzles, can increase acquisition and operating costs. Next, we have training and/or skill requirements. Operating STOVL aircraft requires specialized training and skills for pilots and ground crew. Vertical takeoff and landing or short takeoff and landing operations demand precise control inputs and coordination, increasing training demands and operational complexity.
Continued development of STOVL propulsions leads to adaptations for civilian and urban air mobility flight. better fuel efficiency, reduced emissions, and increased thrust, as well as improved hovering capabilities with better technology. STOVL propulsion, while predominantly used in military applications, have potential for commercial applications. Specifically in urban areas where room is very limited, there are applications for aircraft such as emergency response vehicles and air taxi services. This could open new avenues for rapid, flexible, and efficient urban transportation. The future of STOVL applications is vast in the military industry as well as in civilian applications. With the advent of electric propulsion systems, STOVL applications could become more sustainable, quiet, and suitable for urban environments. There are several challenges that arise in the adoption of STOVL technology in commercial aviation. Noise concerns and infrastructure development are among top concern. But with the advent of new technologies, these can be addressed. STOVL propulsion stands at the forefront of aviation technology. Its application in the military revolutionized warfare, and it has the capability to revolutionize commercial air travel. STOVL technology has the capability of redefining what we know as air travel, making it more accessible, efficient, and environmentally friendly. References.